To figure out the energy required to hold the nucleus together, we can do what's called a nuclear binding energy calculation. And the energy we're going to calculate in this process will be the energy required to overcome those positive repulsion of protons in the nucleus. And it's a pretty big number. The power is achieved by utilizing the strong and sometimes the weak forces, which we're not talking about as much. So it takes a lot of energy, but it is possible to overcome. Strong and weak forces are stronger than both the EM force and gravity, so that's why they become so important. So nuclear binding energy, which gets the symbol E sub B, is used to estimate the force contribution, mostly from the strong force, a little bit from the weak force, just to see like how much energy is actually required to keep the atom together. The binding energy, E sub B, it's the negative of the energy change, the negative of the delta E, if the nucleus is formed directly from the individual protons and neutrons. And I'm sure that's about as clear as mud, so let me give you an example to show you how you can figure out the binding energy yourself for any isotope on the periodic table. Let's calculate the binding energy, E sub B, for deuterium. Deuterium is an isotope of hydrogen. It's hydrogen 2. So hydrogen 2 has a mass number of 2. Hydrogen has 1 proton. So mass number 2 minus 1 for the atomic number means it has 1 neutron. In this process for binding energy, we're going to build this isotope directly from protons and neutrons. So to make hydrogen 2, we're going to need 1 proton and 1 neutron to make that happen. That's going to create the hydrogen 2. And notice the nomenclature there. Protons are often 1,1p like that, and neutrons are often 10n. And we'll come back to this later, but just realize that's the reaction we're going to look at. If you look carefully at the mass of a proton, which is that 1.0078 number, and the mass of the neutron, 1.00865, you'll find that those numbers added together are actually greater than the mass of, in this case, deuterium. So, and this works for all atoms, by the way. The protons plus neutron masses will be greater than the atom that you're actually looking at. So in this case for deuterium, all right, when you add the proton and the neutron up, you get 2.016 or so. And for the deuterium itself, it comes out to be 2.014 or so. So those numbers are not the same. There's actually a mass lost upon going from the proton and neutron to deuterium. Like you would find a delta M, final minus initial. That would be the deuterium minus the proton and neutron. It's the final state minus the initial state. And goodness gracious, we are losing mass. We have lost minus 0.00239 grams per mole. Mass is not conserved. And about this time, you're probably like, boy, Russell, I need my money back because we spent all that time balancing equations, and now you're saying that things aren't even balanced and stuff. And you're like, rah, rah, rah. And I understand because I feel that way too. Well, actually, that mass loss is really important. Einstein has an equation, which is E equals mc squared. And this is a famous equation of his. If you haven't seen it, it's no big deal. But what it is, it's a way to relate the mass of an object to the energy of an object. And how it's usually used is it's a delta E equals delta mc squared. C is the speed of light, 2.998 times 10 to the 8th meters per second. And the delta m part has to be in kilograms to make the units work out. So anyway, we're going to use that little bit of mass loss to figure out the energy used in the process, the energy that was obtained. So what we did right here, in the last slide, it was like minus 0.00239 grams per mole. We're going to turn grams per mole into kilograms per mole, and then we'll multiply that by the speed of light squared. So remember, use 2.998 times 10 to the 8th meters per second for speed of light. We'll multiply by c squared. And when you do that, you get a delta E of minus 2.15 times 10 to the 11th joules per mole. Now, before we go any further, I want to talk about that number because it's pretty spectacular. First of all, it's negative, so it's exothermic, all right? As you make deuterium, you get energy out. That's what the negative sign means. But another thing I want you to think about is the magnitude of this number, because this number is 10 to the 11th joules per mole is way above all the other energies we've looked at so far. For example, if you took a strong acid and a strong base and you reacted them together, it might be, say, 10 to the 6th joules per mole, all right? And you could figure out delta H products minus delta H reactants to figure these kind of things out, by the way. But anyway, those energies are much, much, much less than 10 to the 11th joules per mole. When you make things like deuterium, you are getting an incredible amount of energy out. Not just a little bit, but a lot of energy out. And we'll come back to that here in a little bit. The binding energy is defined as the opposite of the energy change. So basically, you want to turn that negative into a positive, and you end up in kilojoules with a value which is 2.15 times 10 to the 8th kilojoules per mole. And that's just a crazy, crazy amount of energy. So while a lot of the other things we were looking at were, say, 10 to the 3rd kilojoules per mole, this is 10 to the 8th kilojoules per mole. So it's just an incredible amount of energy. Positive version like that, they feel that's the energy saved through stabilization of the strong nuclear force. So it's a pretty massive effect. It's not just a minor effect, it's pretty big. I like to think of these numbers as the justification for why the elements form, because making energy is kind of like making money in our world. And that's a weird way to think about it, but it's true. So as you make money in our world, woohoo, everybody celebrates and drinks champagne or whatever. Well, in the science world, if you can make energy, those are the reactions that usually happen. And this isn't making just a little bit of energy, this is making a lot of energy. So this is the reason why the elements form. So much energy is created that you end up then making all the elements you can, basically. That's why we have hydrogen and helium and lithium and carbon, et cetera, et cetera. And we don't have just protons and neutrons or pure energy for that matter around. A lot of times they'll figure out the binding energy per nucleon, and a nucleon is literally a subatomic particle in the nucleus. So basically count up the number of protons and neutrons, and that's going to be the number of nucleons. So in our example, we have 1 proton and 1 neutron, or 2 nucleons. So if you take that previous EB and divide it by 2, you get 1.08 times 10 to the 8th kilojoules per mole of nucleons. So for every nucleon you put in, you get that 1.08 times 10 to the 8th kilojoules per mole out. This is literally the strong force contribution to the nucleus. All right, it literally tells you how much energy has been saved, and it's considerable. All right, 10 to the 8th kilojoules per mole per nucleon is a huge savings. This is what the strong force does. It's an amazing force. So in the last slide, we calculated the binding energy per nucleon for deuterium, which is hydrogen 2. And this is a graph that shows the binding energy per nucleus for all different kind of versions. So down here at the bottom, this is where deuterium is. It was 1.08 times 10 to the 8th or whatever. So that's where that value is. And then you'll notice here, there's kind of like a curve, and it goes up to a high point of iron 56. We'll talk about this in a little bit. And then it starts to go down again. You can see all the way over there to uranium 238. And this is a really cool graph for scientists. First of all, we're going to talk later about fusion, which is right there, and fission, which is up in the upper right-hand corner. Lighter elements, smaller atomic numbers, elements use fusion to become more like iron, and heavier than iron elements will use fission to become more like iron. And we'll come back to that here in a little bit. But we're going to talk about what this means. But again, what I want you to see more than anything is that iron 56 is kind of the top of the hill, all right? And you can't go any farther than iron 56. So for example, deuterium could use fusion and more and more times to eventually become iron 56, but then it would have to stop. On the other hand, uranium 238, way over there on the right, it could undergo fission lots and lots of times until it got to iron 56, and then it would stop. So iron 56 is going to be a key to understanding the implications of this binding energy graph. So because iron 56 is the top of the hill, it really is the end point of everything in thermodynamics, all right? You cannot make anything past iron 56, more or less, once you get there. So for example, the sun, all right, the most massive energy source in our solar system, the sun, when it starts to make iron 56, it begins to stop. It no longer can generate the fusion in order to make more energy possible. So iron 56 is kind of the end point. And so if you have any kind of solar cycles or any kind of elements, iron 56 is kind of the final spot. So if you have an element that's less than 26 protons, less than iron, it'll use fusion, which we'll talk about later, to become more like the iron 56. On the other hand, the greater elements like uranium, krypton, molybdenum, etc., they will use fission to become more like iron 56. And if you think about this long enough, you can envision probably one day a universe of nothing more than iron 56. And at that point, all energy would stop because there's no more reason to have anything but iron 56 around, kind of a dark, dreary thing. However, I'd like to remind you that kinetics is a huge factor in this. Having any of these reactions possible takes incredible amounts of energy of activation. And so the time required to have the elements fuse or fission, become visible, is really, really large, all right? And multiple generations of children's are still going to be here, right? Assuming, the thermodynamics is not the end all here of things, but it is kind of an interesting topic to think about. Iron 56 is truly the high point of when you make things in fission and fusion. So this is a question you might see. It says, which of the following nuclei has the highest binding energy per nucleon? And it lists the lithium, a nickel, a helium, and a thorium. This would normally be kind of a difficult question to answer because how do you know? You probably don't have a table of binding energies nearby and stuff, and it's hard to look up. However, if you have to guess, which is basically what I'm forcing you to do in this problem, you want to pick the element which is closest to iron on the periodic table. And if you look at the periodic table, nickel is just a couple of elements away from iron, all right? You add a couple of protons and you'll turn your iron into nickel, or take a couple of protons away from nickel and you'll have iron. So the nickel compound here probably has the highest binding energy per nucleon. Now, I had the advantage of Google. I could look the different values up, and there are the actual binding energies per nucleon in what's called a mega electron volt. And a mega electron volt is equal to that 10 to the 13th joules. It's a massive amount of energy. So just look at the magnitudes of those different numbers right there. Nickel 59, 8.69 mega electron volts, much higher than the lithium at 4.88, the helium at 5.49, or the thorium 232 at 7.63. So again, the elements closest to iron should have the highest binding energy per nucleon.